Hello everyone. Today we're going to show you how you can create models using our standard library components in Dyad. We'll first build a DC motor model using the Dyad standard library components. We'll then test this model by applying a constant voltage to it, and then we'll add a controller to the model, simulate it while varying the controller parameters. With that being said, let's go ahead and get started. So here inside my VS Code, the first thing I want to make sure is that I have the Dyad Studio extension installed inside of my VS Code. Once that's there, I want to go ahead and open up the command palette and select Dyad Create Component Library. When prompted, I will name my library DC Motor Components. And I'll go ahead and save my component library inside of this folder on my desktop. So here I have a VS Code window open with my component library folder structure exposed on the left side. So what we're going to want to do is add the standard libraries to our project. So what I'll do is open up the command palette and start up the Julia REPL. In the Julia REPL, I'll enter the package manager by hitting the close bracket key. And then I will add 3 libraries to my project: block components, rotational components, and electrical components. Once those packages have been added, we can exit the package manager by hitting the backspace key. Okay, now let's go ahead and start creating our models. So on the left side over here, I'm going to expand 2 folders, my Dyad folder as well as my generated folder. So as a reminder, what the Dyad compiler and extension is doing in the background is that it's taking a look at what valid models there are inside this Dyad folder, and it generates corresponding Julia models and Julia files for our Dyad models. So what I'll do is I'm going to create a new model inside of my Dyad folder by right-clicking on the folder and selecting New File. I'm going to name this file dcmotor.dyad. And here I'll include the Dyad definition for our DC model, DC motor model. So here we have our DC motor consisting of 2 electrical pins, a positive one and a negative one, as well as a mechanical spline shaft and a mechanical spline housing. This motor is modeled as a resistance and inductance. The coupling between the electrical and rotational domains occurs via an electromotive force component, otherwise known as an EMF. The voltage across the EMF is proportional to the angular velocity, and the current is proportional to the torque. And the reaction torques on the friction and EMF components are connected to the housing connector. We'll also note that there's a few parameters inside of our model, and all of these parameters are of course used to instantiate the various components. Okay, so now that we've constructed our DC motor model, and we can also see that the corresponding Julia file has been generated for this model, let's create a test for it. In other words, an analysis. What we'll do in this analysis is we'll apply constant voltage across the motor electrical pins. In the Dyad folder, let's create another file. And we'll go ahead and name this file test DC motor load.dyad. The first thing we'll include inside of this file is a model for our test. Here we can see the test model named test DC motor load consists of the motor as well as a ground interface, source, fixed load, load source, and voltage source. Of course, the thing we're kind of interested in here is the voltage being applied to the motor. And in this case, the voltage applied is 1. We also have some equations which dictate the physics of our component. And we have in here some initial conditions, specifically the initial motor current is 0, as well as the initial motor speed is also 0. Here's our test model. Now let's create an analysis to simulate this model. Here we have an analysis called DC motor load analysis. This analysis extends from or inherits the transient analysis type, and the model we're using for this analysis is of course the test DC motor load model that we just created right here. So now let's go ahead and run this model. So down here in the Julia REPL, I'm going to go ahead and import my project by doing a using DC motor components. We will also bring in the plots package as well as the Dyad interface packages to help us visualize our results. Okay, so let's go ahead and run this analysis, and we'll store the result of that analysis inside our result variable right here. And now we can go ahead and plot our result. And here we have it. We have a plot showing the change in motor angle over time, motor speed, and motor current. We can see at the beginning of this simulation, there is no load and the motor accelerates to a steady state speed. Recall that there's friction in the model. That's why we're accelerating to a steady state speed. Once the load kicks in right here, we can see that the motor current increases and the speed drops. So let's say you wanted to plot some other variables inside your model. For example, let's say you were interested in what the motor torque is throughout our simulation. So what we can do here is use this artifacts function to pull out the simplified system from our model. And by doing this, we'll be able to plot a result that we'll be able to index into it to tell it exactly what we want to plot. So in this instance, we want to plot tau, which is the motor torque. And there we have it. We have a plot showing the torque throughout our entire simulation. What we did right now is applied a constant voltage to the motor, and we saw the resulting speed response. Now let's try to add a controller in order to control the speed. We'll use a PID controller and also wire a speed sensor in order to provide the motor speed to the controller. And we'll set the desired motor speed as a constant. So let's go ahead and create another Dyad file inside our Dyad folder right here. And I'm going to name this file test DC motor load controlled.dyad. The first thing I'll include inside of this file is my test model with the controller. So we can see here that this model is very similar to the model that we created earlier under the test DC motor load file, but instead of a constant voltage source, we now have a PID controller integrated into our model. And we can see here, down here, a few parameters associated with our model. Of course, right here, this parameter W_motor is the desired motor speed that the controller will attempt to keep the motor at. And you'll also notice there's a few parameters for the controller inside of our model, specifically controller gain, time constant of the integrator block, time constant of the derivative block, as well as the maximum derivative gain. With this model, let's go ahead and create an analysis for it. So here we have an analysis called DC motor load controlled analysis. This analysis extends or inherits from the transient analysis type, just like before. The model we're using is the test DC motor load controlled model that we just created right here. And then there's also a few parameters inside this analysis. We can see that these parameters inside of this analysis are passed on when creating the model. Therefore, effectively what that means is when we run the analysis, we're able to change these defaults if we'd like. Let's go ahead and run this analysis with a gain value of 0.1 instead of 0.5, and then we'll leave all these defaults. So I'll go ahead and call the analysis right here, and I'll pass a keyword argument to set the controller gain value to 0.1. Once analysis is done, let's go ahead and plot our results. So just like before, I'm going to go ahead and pull out the simplified system from our result, and then I'm going to set up this keyword argument variable to help me with my plotting. Inside of this keyword argument variable, we can see that what I want to plot are the indices for the velocity of the motor as well as the controller output. Then I can simply plot my result using that keyword argument variable, like so. So here we have it. We see the results from our simulation. We can see the control signal coming out of the controller as well as the speed signal coming from the motor. Recall that the desired speed is 1, which is right about up here. This controller does an okay job of getting the motor speed up to 1, but as we can see, it doesn't get that close and it's a little bit unstable. So now let's go ahead and see what would happen if we ran this same model, but instead set the gain value to 0.5. So what I can do is use this plotting command right here, What this command will do is it will run the DC motor load controlled analysis with a gain value of 0.5, and we'll go ahead and plot the result of this on the same plot that we have up here. And that's what this exclamation mark means. Just create a new plot, combine it with the previous plot. Okay, so with that, I'll go ahead and run that command. And on the plot here, we can see the results from both runs. We see the blue line here, which is our simulation with a gain value of 0.1. And then we also see the red line here, which is our simulation with the gain value of 0.5. So we can see here that by increasing the gain value by just a bit, we get a much better speed response for our simulation. Now, let's see if we can tune this controller automatically. We'll go ahead and use some PID auto-tuning analysis for this next step. So what I'm going to want to do is add another package to my project. I'll go ahead and enter the package manager in my REPL. And what I'm going to add is Dyad control systems. Once that's added, I'll exit the package manager by hitting the backspace key. So now let's create our auto-tuning analysis. In the Dyad folder, I'm going to create a new file, and I'm going to name this file tuning analysis.dyad. So here's the code, the Dyad code for our DC motor tuning analysis. We can see here that the analysis extends the PID auto-tuning analysis from the Dyad control system package. Here are the arguments we're passing to this analysis. And we can see here that the model we're using is the test DC motor controlled model that we created earlier, right over here. So we can go ahead and run this analysis inside my Julia REPL. I'll store my analysis inside my variable asol right here. Once the analysis is done, we're going to go ahead and use the artifacts function like before, but this time we're going to pull out the optimized parameters from our analysis. We'll go ahead and use this command right here to pull out the K, Ti, Td, and Tf values from our analysis. And then finally, we're going to go ahead and calculate ND by dividing Td by Tf. And if you're wondering why we're doing this, why we're interested in these values right here, recall that these are the values that we're going to be able to pass to our controller during the simulation, right? So we did this auto-tuning analysis to pull out these 4 parameters that we need, and we'll be able to pass them to our analysis to simulate. Using this command, we're going to go ahead and run the analysis that we did before with the K value of 0.5, and we'll go ahead and plot that. So what we'll do first here is we'll go ahead and plot our previous DC motor load controlled analysis results with a gain value of 0.5. And also on this plot, we'll include the DC motor load controlled analysis, but we'll now feed in the 4 parameters we just obtained from our auto-tuning analysis. So here we can see the initial controller in blue. It does an okay job of keeping the motor at a speed of 1, but we can see here the tuned version of the controller in red does a much, much better job than our nominal model. And that concludes today's lesson. What we did was we first created a DC motor model using standard library components in Dyad. We then tested this DC motor model by applying a constant voltage of 1 to it. Then we went ahead and added a controller into our model to see how well it could keep our motor at the value of 1, the motor speed value at 1. And then finally, we did some tuning analysis to obtain the optimal parameters for our controller, and we saw the results of that tuning. Thanks for joining today.